today's lecture will talk about a very important and useful feature provided by the C programming language, and that's the notion of structures. So essentially the use of structures is that using structures you can put several pieces of related information at the same place in a single variable instead of spreading them around the program in different variables. And so as you can see, a structure is also a composite type because a structure is comprised of smaller units of data. However, the difference between an array and a structure is the following. An array is also a composite type like structures, except that all elements of an array are of the same type, whereas with structures we can have different elements of different types. The other difference between arrays and structures is that in arrays the individual elements of the array are accessed using a numerical index, which is an integer, whereas the different elements in a structure are accessed by different names. We can give different names to different elements, and that makes it very useful. And as I said, the other difference is that the different elements of a structure can have different types, whereas the elements of an array all have to have the same type. So let's consider a simple example where we might want to use structures. So suppose we are writing a program that is maintaining student records and so on, and so we need to maintain various pieces of information about every student. So we could define a structure for storing the information about a student, and the structure declaration might look like this. So this entire declaration defines a new type whose name is struct student. The keyword struct indicates that this is a structure that we are defining, and the word student is a name for the structure type, and then within braces follow the declarations of the various components of the structure, and these can have arbitrary types. So the first element in this case is name. That's the name of the element which will store the name of the student, and the type of this element is an array of 20 characters. So that shows that you can have arbitrary types inside the structure, so the elements can really have any other type. The next element of the structure is a field called roll number, which is of type int. So this will probably be used to store the roll number of the student. And finally we have an array of two integers for storing maybe the exam marks of the particular student. Before we look at such complex structures, let's first look at some examples involving simpler structures. So suppose we need to write a program that deals with complex numbers. So as you already know, a complex number has two parts, a real part and an imaginary part. And to represent a complex number, essentially we need to store both these parts. So the ideal representation of a complex number would be where a single variable stores both these parts, and so therefore we declare a struct complex which defines a new type for complex numbers, and you can see that there are two elements or two fields of the structure with names real and image, and both are of type float. So this complex number will have two parts, a real part and an imaginary part, which are both floating point numbers. So once we have a declaration like this, we can now declare as many variables of this type as we want. So this declaration does not declare any new variables, it just declares a new type. This is the first time that we are seeing such a notion. But once we have declared such a type, the type struct complex is now available to us, and we can declare any number of variables of this type. So for example, this declaration declares two variables C1 and C2, which are both of type struct complex, which means that C1 as well as C2 will both have their own real parts and their own imaginary parts. Now we use the dot operator to access individual fields of a structure. So obviously if we are given a structure, we need to be able to manipulate the different fields of that structure, and the dot operator is used to obtain an element of a structure given the structure itself. So as an example, let's assume the same struct complex declaration. So let's say C1 is a variable which we have declared to be of type struct complex, and now we can access its real and imaginary parts as shown. So essentially C1.real will denote the real part of the structure C1, and C1.image will denote the imaginary part of the structure. So essentially C1 is a variable which comprises of two boxes, both large enough to hold an integer, and the names of these boxes you could think of as being C1.real and C1.image. And as these assignment statements show, these expressions can be used on either side of an assignment. So C1.real is equal to 10.53 would essentially assign the value of the real part of the structure C1 to 10.53, and C2.image assigned C1.image will copy the value of C1.image, that is the imaginary part of the variable C1, to the imaginary part of the variable C2. So C2 is also, let's assume, is of a similar type. So this assignment statement will copy this value to this value. So whatever this happened to be, let's say 5.0, then this also becomes 5.0. And as you can see, the types of these expressions would be the types declared for these fields. So we had declared real to be of type float and image also to be of type float, and therefore C1.real will have the type float and C2.image will also have the type float. Now structures are full-fledged types, and we can do all the usual kinds of operations that we can do with other types. In particular, we can pass structures as arguments, and we can also write functions which return structures as return values. So as an example for passing structures as arguments and returning structures as return values, let's consider a function to add two complex numbers. So we have this function add complex, which is supposed to add two complex numbers. There are two parameters, C1 and C2, both of type struct complex, and the return type is also struct complex. Now how do you add two complex numbers? Well, that's very easy. You just have to add up the real parts and the imaginary parts separately. So that's what this function does. It declares a local variable called sum of type struct complex, and sum.real is assigned the value C1.real plus C2.real, and sum.image is assigned the value C1.image plus C2.image, and finally the value of sum is returned. So here is a function add complex to add the two complex numbers. It has two parameters, C1 and C2. Both are of type struct complex, that is C1 and C2 are both complex numbers, and the return type is also struct complex. That is, we are going to return another complex numbers from this function. So it declares a local variable called sum, which is also of type struct complex, and now to add C1 and C2, all we need to do is to separately add the real and imaginary parts, and that's what this two lines of code are doing. The variable sum after these two assignments will represent the complex number C1 plus C2. So sum.real is C1.real plus C2.real, sum.image is C1.image plus C2.image, and finally function returns the value of sum, which is C1 plus C2. Okay, now one thing that we need to understand about structures as opposed to arrays are that structures are passed by value. That is, when I declare a structure variable, that variable represents the structure itself and not the address of that structure. And therefore, when a structure is passed as an argument to a function, its value is copied to the parameter, and its value is nothing but the values of all its components or all of its fields. So the values of all its fields are copied to the corresponding spaces in the parameter. And this is different than for arrays. For arrays, as you know, when you pass an array, what is actually getting passed is just the starting address of the array and not the values of the elements of the array. And therefore, the implication of this fact is that if the called function modifies the field of the parameter which happened to be a structure, then the effect is not visible in the called function. We'll see an example using a variant of the add complex function that we just saw. And similarly, when a structure is returned from a function, a copy of its value is made, and that copy is what is returned to the calling function. So let's see an example of these facts using a slightly different version of the same add complex function that we just wrote. Here we don't have a local variable sum, and what is being done is that the sum is being computed in the parameter C1 itself. So C1.real plus equal to C2.real, that means the value of C2.real is added to the existing value of C1.real, and similarly C2.image is added to C1.image, and finally the value of C1 is returned. And let's say this is how this function is getting called from the main program. We have three local variables C1, C2, C3 of main, and we call add complex C1, C2, and the return value is stored in the variable C3. So let's assume that just when the function add complex is called, this is what the three variables C1, C2, C3 of the main function look like. C1 has a real part and imaginary part, and similarly C2, C3. And let's say C1 is 5 plus 7i and C2 is 6 plus 3i, and C3 is uninitialized. So when the function is called, as you know, what happens first is that space is created for the parameters of the called function, which in this case happen to be C1 and C2. So the space for parameter C1 and parameter C2 of the function add complex has been created. Next, what is going to happen is that the values of the arguments are copied into the corresponding parameters. So the arguments are expression C1 and C2. When C1 is evaluated, it evaluates to the entire structure 5 and 7, and similarly when C2 is evaluated, it evaluates to the structure containing 6 and 3. So when this copy happens, this structure value is copied to C1 of add complex, and this value of C2 is copied to the parameter C2 of add complex. So C1 gets the value 5 plus 7i, and C2 gets the value 6 plus 3i. Now when this statement is executed, C1.real is plus equal to C2.real, we are executing within the function add complex, and therefore C1 refers to this C1 and not to this C1, and similarly C2 refers to this C2 and not to this C2. So this statement will modify the real part of this C1, which is this value. So this value will become 5 plus 6, that's 11, and the imaginary part will become 7 plus 3, which is 10. So in the next step, C1.real becomes 11, and in the next step, C1.imaginary becomes 10, and finally the value of C1 is returned. So when this value of C1 is returned, this value will be copied into the variable which is going to hold the return value, in this case C3, and so this copy is made, and now the function add complex has returned. So as you know, the space for its local variables and parameters will be removed or deallocated, so these variables will now cease to exist, and C3 has become the sum of C1 and C2. But the important point is that these changes to C1 did not affect the value of the variable C1 in the calling function. Now let's look at some other operations on structures. And the basic operation that we can do is that a structure can be assigned to another structure variable of the same type. So let's say again C1 and C2 are variables of type struct complex, that is, they are complex numbers. So this assignment is valid. Note that the left hand side is a variable which is of a structure type, and the right hand side is also an expression which has the same structure type. So the C1 assigned C2 is valid, and whatever is the value of the complex number C2, that gets copied into the complex number C1. Again, contrast this with arrays. With arrays, an array variable cannot appear on the left hand side of an assignment expression, because an array variable as an expression denotes the starting address of the array and not the contents of the array itself. And the starting address of an array is fixed. It is assigned by the compiler, that can't be changed, and therefore an array variable cannot appear on the left hand side of an assignment. Whereas for in the case of structures, a structure variable represents the contents of the structure and not its starting address, and therefore it can appear on the left side of an assignment like this. So if C2 happen to have the value 5 plus 7i, then after this assignment statement, C1 will also have the value 5 plus 7i, and this value gets copied here. Okay, let's now look at some more complex structures than the simple structures that we have seen. So let's recall the student structure that we already saw, struct student, which contains 3 fields: the name of the student, the roll number, and the 2 exam marks. And let's assume that we declared a variable s of type struct students. Now what does s.exam marks represent? S.exam marks represent this component of the structure s, which is an array. So therefore s.exam marks represents really a pointer to an array of 2 integers. And so s.exam_marks 0 and s.exam_max1 will represent the 2 elements of this array. Note that s.exam_marks itself is an array, and therefore as for arrays it represents the starting address of the array rather than the contents of the array. So if we now happen to pass s.exam_marks as an argument to a function, then it is the starting address of this array which is being passed. So if we want to look at this structure pictorially, this is what it looks like. It has an array of 20 characters, which is the field called name, and then it has a single integer called roll number, and then it has an array of 2 integers called exam marks. And s is the name of the entire structure, that's the variable, and so therefore s.name is an array type. It is an array of 20 characters, and therefore this variable itself represents the starting address of this array. This expression s.name represents the starting address of this array, and again it cannot appear on the left side of an assignment because the starting address of this array is fixed. But s.roll number can assign on the left side of an assignment because this represents just an integer variable, this particular variable. And so this could be assigned to the value 123 or whatever else it happens to be. And similarly s.exam_marks represents an array, and therefore the starting address of that array. And so the usual rules for arrays will apply, whereas for s.roll number the rules for integers would apply. Okay, now we can also have structures inside structures. So we can have one structure type as a field or a component of another more complex structure type. As an example, consider a program that deals with geometric objects. So for this program we need types to represent points, lines, and so on and so forth. So we could represent a point by just its xy coordinates. So here is a declaration for a structure which represents a point. Now a line perhaps is represented by its 2 endpoints, or a line segment is represented by its 2 endpoints, which are both points. So this structure contains 2 fields P1, P2, which are of type struct point. So therefore if you look at a pictorial representation of a line, it will have inside it 2 structures called P1 and P2, and these in turn contain 2 fields each, which are called x and y, x and y. So now if we have declared L as a variable of struct line, then L.P1 represents this entire structure, and therefore L.P1.x represents the x part or the x coordinate of this particular point P1 of the line L, and similarly L.P2.y will represent the y coordinate of the second endpoint of the line, and so on and so forth. We could also have arrays of structures. Not only could we have structures containing arrays, but we could also have arrays of structures, and those structures themselves in turn could actually have other arrays within them. So you can see that using these kinds of building blocks we can we can build some very complicated data structures. So let's come back to the student structure that we were talking about earlier. Now suppose a program needs to maintain records of all the students in a particular class. So we probably need to maintain the student records of the various students in an array. So here we have declared an array called my students, which is of size 100, and the type of each element of the array my students is struct student. So therefore my students is an array, each of whose element is a student structure. And so for example, if I have this expression my students I dot roll number, so my students I gives the ith element of the array my students, which happens to be a student structure, and therefore my students I dot roll number denotes the roll number of the ith student in this array, and similarly my students I dot name would represent the name of the ith student, and so on and so forth. We can also of course have pointers to structures, just like we can have pointers to other kinds of variables, and these pointers to structures work in the same ways that pointers to other kinds of variables work. So for example, suppose we have a variable C1 of type struct complex, and what we are declaring here is a variable P which is of type struct complex star, and what that means is that P has a type which is a pointer to a struct complex. And now what we are doing is star P1 dot real assign 10. So what does this mean? This should be star P, not star P1. So P is a pointer to a structure, and so therefore star P represents that structure, and therefore star P dot real represents the field called real of that structure. So in terms of a picture, this is what is really happening here. The C1 variable C1 is a structure with a real part and an imaginary part, and the variable P is a pointer which points to the structure C1, and so star P will represent this structure, and therefore star P dot real will represent this field of the structure, and that is getting assigned the value 10. So this assignment statement causes C1 dot real to become 10 because P points to the variable C1, and therefore star P dot real represents the same thing as C1 dot real. Now this is a very common operation that we first dereference a pointer to obtain the structure to which the pointer points, and then refer to a particular field of that structure. So for these two operators applied together, C provides a shortcut. So the operator arrow, which consists of a minus mark followed by a greater than sign, denotes a combination of the star and dot operator, and this is how we use it. P arrow real is exactly the same as star P dot real. So we could have written this statement as P arrow real assign 10, and of course we could also have used it on the left hand side, on the right hand side of an assignment, and so on and so forth. Okay, having looked at structures, we'll wrap up this lecture by briefly talking about input and output from files. So far we have been doing all our input output from the terminal, that is all the inputs that the program expected the user had to type at the terminal, and all the output again went back to a terminal. Now in general, when we are writing programs that require large number of inputs and the output is also voluminous, we want the program to be able to directly read and write files instead of expecting all the input from the terminal, and that of course can be done, and that is actually very similar to the way input and output is done from the terminal. We'll shortly see the library functions for doing that, but the basic difference between I/O from a terminal and I/O from a file is that before we can read or write a file from our C program, we need to open it first. And when we open a file, what we get is what is known as a file handle, a handle for a file, or in C it's also called a file pointer. The type of this file pointer or file handle in C is file star. File is a type which is defined by the standard IO library of C, and file star is the type for the file handle which is returned to us when we open a file. And now once we have opened the file and obtained a file handle for the file, then we can read or write to the file depending on how the file was opened. And whenever we want to read or write the file, we need to specify the file handle for the file instead of the file name for the file in every call. When we open the file, that is the only time that we really specify the file handle for the file name for the file. And finally, when the program is finished reading or writing the file, it should close the file again by specifying the file handle. We'll see the functions to do all this in the next slide. So first, opening the file is easy. You need to use the fopen function of the standard IO library. There are two arguments. The first is a string, which is the name of the file that we wish to open, and the second is a mode, again a string, which represents the kind of operations that we are going to do to the file. For example, are we going to read the file or write the file, and so on and so forth. And the return type is file star, which, as we have seen, is the type for the file handle. Now this mode should be a string containing just the character R if you want to read the file. It should be W if the file is to be written. So if we specify W as the mode for the file, that means that the file will be created automatically if it does not already exist, and if it does already exist, then whatever data it already contains will be deleted, and whatever now this program writes will be the only surviving contents of the file. So that means the existing contents of the file will be removed, and whatever the data our program writes to this file, that will overwrite the existing contents. And if we don't want to do that, if we don't want to delete the existing contents of the file, we can open the file for appending by specifying string containing A as the mode, and in that case whatever data the program writes will be appended to the file. And of course, again, if the file does not already exist, then the file will be created. But when the mode is R, when we want to read the file, then the file must already exist, otherwise it will be an error and will not get a proper file handle. So if for whatever reason the file cannot be opened, for example, we are trying to open it for reading and the file does not exist, or if we are trying to open the file for writing and we don't have permissions to write to the file, or maybe the file does not exist and we don't have permission to create the file, and so on, or maybe we are trying to read the file and we don't have permission to read the file. If anything goes wrong and the file cannot be opened, then fopen returns a special pointer value null, which we'll also have occasion to see in the next lecture. This is a very useful pointer value, but essentially this is a special pointer value. It does not point to any legal memory location. So the point is that whenever we open a file, we must check the file handle that has been obtained, and if that is equal to null, that means we were not able to successfully open the file, and so we should print an error message and the program should exit if that is what is appropriate. So once we have obtained the file handle to a file, we can now use this file handle for doing actual I/O on the file, and the functions for reading and writing files, as you'll see, are very similar to the ones for reading and writing from the terminal. For example, we have the scanf function, which is exactly the same as the scanf function that we have already seen. So the scanf function reads from the terminal, whereas the scanf function reads from a file. The only difference in the arguments is that the first argument has to be the file pointer, and then the format string as usual. The format string has exactly the same meaning as in scanf. Then the function fgetC is again the same as the function getChar for reading one character from the terminal. This also reads and returns one character from the file, and the argument is the file pointer. fgetS is the equivalent of the getS function. You specify pointer to a character array where the data has to be read. Now there are two additional arguments in this case. The third argument is the file pointer, and the second argument is the size of this array which has been specified here, and the fgetS function ensures that no more than this many bytes are actually returned to this array. Otherwise, of course, as you know, there is an array bounds violation
getters function does not actually check that array bounds violation. For writing to a file, the functions are again similar to the functions for writing to the terminal. The fprintf function is exactly the same as the printf function, except that there is an extra first argument, which is the file pointer of the file to which we want to write, and this file pointer must be opened for writing or for appending. And similar to the putchar function, we have the fputc function, which takes a character and additionally a file pointer of the file to which this character has to be written. And fputs function is the equivalent of the puts function, which writes a string to a particular file. And finally, this fclose function is used to close the file. As I said, once the program is finished reading or writing the file, it should properly close the file, and you use the fclose function for doing that. All you need to specify is the file handle or the file pointer as the argument. Okay, so this is the end of this lecture, but before we stop, here is a simple exercise for you to try using the concepts that we have learned in the last couple of lectures. So the exercise is to write a program that will read an input file name and an output file name from the terminal. That is, the user will type the name of the input file and the output file. The input file is supposed to contain student records of the type that we just saw, one per line. So the program will read the student records from the file, sort the records by roll number using the sorting algorithm that we have already seen, and finally write the sorted student records in the order of the roll number to the output file. In the next lecture, we will talk about another very important technique in programming, and that's the technique of dynamic memory allocation, which allows us to overcome some of the limitations of arrays.